minutes I don't have a strict plan as to what I want to do. It will depend on how you guys respond. Yeah, actually respond and stuff. So, uh, any doubts in any definition or anything, or did any of you try any of the
Yeah.
problems?
Can you repeat from group subgroups and group representation to the master briefly?
Right. So, not a group representation. A representation is a completely different thing.
Oh yeah, yeah.
So
Presentation.
yeah. So the so you have this sense of that every group is generated by some element, right? You know, for example, all the elements of the group generate the group. So for any group, we can get a set of generators. But then, so if so, let's say let's take for example this group. Let's say Z mod 5Z cross Z mod let's say 10Z. So can you tell me which elements generate this? I mean, first of all, is the notation clear what this means?
Yeah. No. Can you please revise generator also?
Right. So, okay. So, uh, trivial example is Z mod NZ, which is generated by one, right? You get one plus you get zero, one plus one plus one plus one, and so on. So, one one generates Z mod NZ. I mean, generator is not really too complicated. So, yeah, here is the formal definition. Subset S generates a group G if the smallest subgroup of G, which contains that subset, is G itself. Uh, so, can you see that Z mod NZ is generated by one?
Uh, just go back to the definition.
Cool.
Wait a second. So we say that a group G is generated by a subset S, right?
Yeah,
Okay. So if if this definition hold,
yeah, but this definition is the more general one. Here, you take any subset of the group and see the subgroup generated by that subset. We want that subgroup to be the whole group. So, I mean,
okay.
This is a toy example, right? Z mod NZ is generated by
Yes.
one. Okay, let me ask this. Let's say this is generated by A. What are the possible values of A? So we want we want this 0, comma A, comma 2A up to something is equal to 0, comma 1, comma n minus 1. And we are looking at things modulo n.
Okay. Yes,
Okay,
by the definition of this group.
let's do this. So Z mod 4Z, right, has four
Yes.
elements
Yes.
0, uh, 0, 1, 2, and so what is the subgroup generated by 0?
Um, zero, then zero plus. No, this is a zero.
The 0, yeah.
Yeah.
1 generates everything.
Yes.
What
Yeah.
about 2?
This group is defined on addition.
Yeah,
Okay. Yeah. Because multiplication does not exist. No, is not a group.
I mean, for multiplication to be a group, you will have to remove 0 and 2.
Yeah.
Okay, so
Then by
what is the
two,
subgroup lattice?
we, yeah. So two plus one,
Not 2
and
plus 1, right? Only 2 you can use.
okay. Yeah. So zero and two, because if we take four, four mod four is zero.
And 3 also generates this group, right?
Which group?
This group, right? 0, 3, 6, 9 is same as
Yes.
this.
Yes.
I mean, modulo 4. Cool.
Yes.
So, in general, if Z mod nz is generated by A, what can A be? And what are the possible values of A? Clearly, 1, A equal to 1 works.
Yes.
And
We have to what we have to do here. We have to generate group
we have
with
to
A.
generate the whole group using A. So,
Okay.
for example, Z mod 4J is generated by can be generated by both 1 and 3.
Yes. And here also, if A is equal to one, this group is generated, and we have to find one
Yeah,
other A.
we have to find all the possible values of A that generate this group. So, if you have, so this is very number theoretic, and if you have
Yes.
done some, if if you have done like some formal number theory, this is called, I think this is called complete residue set. A
Yeah. Yeah.
generates the complete residue set. Yeah,
Yes.
right. So what are the values of A?
Um, like the residue set of n.
No, I am asking which values of A generate the whole group.
Okay, wait a second. Let me think.
So like for n equal to 4, the answers are A equal to 1 and 3.
Yeah.
Someone asked if the class. No, I don't think this class is not for PRM. This class does not have, to be honest, any intersection with PRM. Maybe some small number theory things, but mostly not. So should we try more examples? Let's say. So first of all, Z
Yeah.
mod
More
P Z
examples would help. Yes.
for P prime.
Here also, one will generate, I guess.
Yeah. Other than that, sorry.
Other than that, if we try two, what happens? Um.
So here is the thing I want you to prove. Everything other than 0 generates this.
Oh,
Everything
okay.
other than 0.
Yeah, maybe because yeah, that residue thing, because all the things will cycle.
Yeah, exactly. And the cycles will cover all possible residues.
Yeah, yeah. Because those are the equivalence classes.
Yeah, exactly.
Yeah, yeah, got it.
So does that give you any ideas about how to approach this? Or okay, let's go. Let's say, by the way, this is like not, if you are trying to think of something too complicated, then don't, because this is not something too complicated. This is something. small. But small is not the
This
best word, but
in
yeah.
this p square, maybe this is powers of p, which are smaller than p square, like 0, 1, and p.
Sorry, what are you trying to say? The possible values of AR?
Um, no, 0 will not work. Okay, so 1 will work, and
Yeah.
p will work.
One will always work.
Yes, and p will
P
always
will
p
P
will
work.
p, yeah, I guess p will work. Yes.
So here P equal to 2.
Oh, here it does not work. Okay.
In general also it won't, because you have P to P. Wait, let me add a 0. Up to P minus 1 times P,
P
right?
minus 1. Yes.
Nothing else. But
P
this has
plus
P
1.
square elements.
P plus 1 will work, I guess.
Yeah, P plus 1 will work. P plus 1, yeah,
Just
P
like
plus 1 will work.
there are three. Yeah. P. It's like uh, 0 times p plus 1. No. P plus 1, then 2 times p plus 1, and 3 times p plus 1.
Okay.
Uh, Now, more I have to find. These are the just two.
So let's try another case.
In
Like,
that case, 4, where we tried 4, there were just two. So
yeah.
maybe in general case.
So let me give you a hint. Today. The number of A is phi of n.
Oh, okay. So pi of p square. Phi of p square.
Yeah, of course. But what are the possible A's? That is just the number of A.
Yeah.
So okay. So uh, what does phi of n count? I mean,
Yeah,
what
number
is
of
phi of n count?
number of integers, positive integers which are less than and relatively prime to n.
Yeah. Can you see that all those A work? Any A which is
Yes.
co-prime to n works?
Yes, yes.
Cool.
Yeah, I can see. Yeah,
Uh,
that is clear.
yeah. Right. So yeah, that was the. I think so. Generator is clear, right? For now.
Yes, clear.
Right. So
Also, this was just it. So like all the numbers which were relatively prime to n will work.
yeah, exactly. So those are
And
the
in the
generators.
prime, yeah. So in the prime case, this was easier because all the numbers were relatively prime.
Yeah. So
Okay, got it.
let's let's shift to a slightly more non-trivial group, right? D2n. Now, clearly D2n is generated by S and R, which is the rotations and the reflections, right?
Yes.
But so think of the opposite problem. Suppose we are given that there is a group which is generated by these two elements. Find the group. That is a harder problem, right? And so, okay, maybe let's clear that. Yeah. So the thing is, if I don't give you any constraints on SNR, then you can produce infinitely many things, right? S, SS, SRS, all possible strings of R and S.
Uh, how?
So let's say if I let's say I tell you that G is generated by two things, A and B.
Okay.
Can you find G?
Here, what is the operation?
Operation, I mean, no operation, uh, star, some
Yeah,
random
star. Okay.
operation.
Okay.
So you cannot solve this, right? Because let's say for the dihedral case, because the dihedral group is also generated by two elements. But if I only tell you that two elements generate this, this is that is not enough
Oh yeah,
information
we
to
can just
actually figure out,
do anything. Right. Right.
right? If only
Yes,
this
that
much
is.
information is given, if only
Okay.
this much information is given, you can create infinitely many elements, like A, one A, A, and all possible strings, A, B, A, B, A, B, A inverse, B, A inverse, random
So
strings, right?
these will be
So
the elements of the group, like one A.
yeah, this will be the elements of the group if no more information is given, right? But
Okay.
for let's say the dihedral case, we have more information, right? We know that r power n is 1, so I cannot have too many r's. We also know that s square is 1 because a reflection applied twice is the identity and the rotation applied n times is the identity, right? Now it turns out that even this information is not sufficient to
To find
figure
the
out
unique group.
this group. Yeah. So you also need this.
Oh,
If you have this, then you can. So if you have that S and R generate the set, sorry, generate the group, and these are the constraints on S and R, right?
okay.
Then that group can be figured. Even though in general, so so a group presentation looks like this. You have a set of generators, and then you have a bunch of constraints.
What is
So
this
for
S?
so S refers to reflection, a reflection about a fixed
No,
identity.
no, that is clear. That capital S in the previous line.
Oh, this is
This.
the set of generators.
Oh, okay. So the set which contains is R1, R2.
So
No, no.
R1, R2
These
are
R1,
the
R2 are.
constraints. You can just like compare these two equations, right? This thing generates D, sorry, generates the group, and these are the constraints.
So this is a way to write group.
Yeah, this is a way to represent, not represent, present a group,
Oh, okay.
right? Any other
Okay.
doubts of
No, pretty clear so far.
cool. uh, other people or any general notions about any problem from the PDF that you tried, which you could not solve? Okay, cool. So okay, let's do a since we did all this stuff with generators, let's try. No, perhaps I should wait. Yeah, I'll just go over the. So something which I did not cover last time in the session was this definition of a subgroup lattice. So let's try that. Let's try to find the subgroup lattice for some groups. So
What
okay,
what is that Damit? Damit means Damit is some book. Damit and Foote.
yeah, David and Foot is the name of the book from which I
Oh,
have taken
okay.
the problem.
Yeah, yeah, got it.
Cool. So okay, let's. Let's take a let's say 6 instead. This is 0, 1, 2, 3, 4. So, what are the subgroups of this? First the trivial subgroup,
Yeah, zero. Yes.
then
One.
okay, if you put so first of all you have to put the identity, right? Because it has to be a group. Now,
Oh, yeah.
if I put if I put 1, then 1 plus 1 must also be there. 1 plus 1 plus 1 must also be there because this has to be closed under addition, right?
Yes. Yes. Yes.
So if I put 1, then I get the whole group.
Uh, uh, if we want a two group subgroup, two element subgroups, then it does not exist.
Yeah, it exists, right? This is a two element subgroup.
Three, zero and three. You have written.
Yeah, yeah.
Okay.
This is a two element subgroup, right?
Uh, but what is the inverse of 3 here?
Itself,
Oh, okay. So this is okay. We are considering mod 6. Okay,
3
I
plus
got it.
3, 3 plus 3 is 0 mod 6, yeah.
Yes, yes.
Right. Okay, let's put 2. Does this suffice?
Uh, no, because here the inverse of 2 is what 4.
Yeah.
Yeah, now it can
Now the
suffice.
cool. And Z mod 6, those are all subgroups of Z mod 6. Those are the only subgroups, right? So
Yeah, yeah. This is clear.
I I hope you remember what isomorphism is. This is isomorphic
Yes, yes.
to
Yeah,
Z
bijective
mod.
function if they exist.
This is isomorphic to Z mod 2Z. This is isomorphic to Z mod 3Z, right?
Yes.
Nice. So this is clear to everyone, right?
Yeah, yeah. Isomorphism. Yeah, this isomorphism you're talking about.
Yeah,
Yeah,
this
this is clear.
isomorphism and in general, cool. So the subgroup lattice, right? So the subgroup lattice of this group looks like this: 0, then you have 0. I will explain what a subgroup lattice is, but let me just add a diagram. Actually, I don't need arrows, but yeah, sure. So arrows represent that this is contained in this. Arrows represent containment.
Uh, what is contained in what?
So if there
Zero
is
is
an arrow
contained in
from
the
A to
two,
B, if there is an arrow from A to B, that means that A is contained in B.
and A is a subgroup.
Yeah, A, B are subgroups, and we only do the, I can also add a containment here, but that's not really required.
Okay. Oh, so it's basically uh, says that if if all the elements of A are in B, then A is contained in B.
Yeah, exactly. A is contained
Okay.
in B, A is a subgroup of B, whatever you
Yeah.
want to call it.
Okay.
So, something interesting I want to talk about is okay, let's do this. This is size 6, this is size 2, this is 3, and this is 1. Does this diagram remind you of something? I mean, yeah, perhaps so in lower classes you do this division trees, and
Yes.
there you
The
write it
factorization
like on
tree.
a number.
Yes. Right.
Yeah, exactly. Factorization tree, division tree. So in fact, what I want you to prove is, in
This
general,
like
that
factorization of group.
sorry, what?
So you mean that this is like factorization of group?
Uh, I don't want to call it factorization because like, factorization of group is has a very distinct definition. But yeah, in some sense,
Oh,
you
okay.
are counting down all the subgroups of the group and
Connecting
uh,
them by
uh,
values.
putting them in a poset fashion. So okay,
Yeah.
do you guys know what a poset is? All right.
Me, no, I don't know.
Okay, that's fine. Let's not get into that. So a poset is a partially ordered set if you want to, if at any point you want to do it. Right.
Yeah, okay,
So
let's
the
first code
group
this.
lattice, so the subgroup lattice of Z mod 6Z looks like the, whatever you call division tree or factorization tree of 6. What I want you to prove is that in general, the subgroup lattice of Z mod NZ, whatever this will be, you know, something, and in the end you have a zero. This, sorry, this thing will look like the division tree of N. So let's try one more example. Let's say Z mod 12, and in Z mod 12 Z you have, okay, let me do this, 0 and 6,
Yeah, 0 to 11.
0, 4, 8. Wait, I think I messed up. Sorry. What are the other subgroups of this? I forgot a 6 here.
You have to make by by using 0 and 1. Then we
What
must
is this?
include
This whole group, na?
what?
Zero and 1 is this whole group, right? 0 and 1. If a group has zero, if a subgroup has 0 and 1, it needs to contain all of the elements, right?
Oh, so this will oh yeah, yeah. You're right.
Yeah, I think this is it. Yeah. So for reference, there is the factorization tree of 6. Sorry,
3
12.
sure. But 4 is different. So in the general case, I guess we have to first write that uh, factorization of n.
Yeah, so I will leave that as exercise because I won't cover to anything about subgroup lattice in this lecture. So
Okay.
exercise is to prove that the subgroup lattice of Z mod and Z looks like the factorization tree of Z mod and Z. And if you have noticed something that this has 12 elements, this has
Yes.
6 elements, this has 4 elements, this has 2 elements, same as this tree. Right.
Yes. Yes.
Cool. So I'll start with the actual session for now. Agar, you can stop and restart if you want to. The
Okay.
recording.